Okay, in this video we're going to be looking at how to estimate a population proportion. So this is one of the videos that we're going to be talking about that deals with estimation. Okay, and we're going to be talking about confidence intervals as well. Alright, now to begin this particular concept of confidence intervals, we need to define some terms, starting with a point estimate. And a point estimate is nothing but a single value or point used to estimate a population parameter. It is a single value that is used to estimate a population parameter. And that population parameter could be a population proportion or a population mean or a population standard deviation. Okay. Now, in this case, we're dealing with a population proportion, so the sample proportion and the sample proportion is notation is going to be p hat. P hat represents the sample proportion, and that is the best point estimate of a population parameter. And a population parameter is denoted by the lowercase p. Okay? Because in real life, if, let's say for example, if I wanted to find out the percentage of students that were successful in college algebra, unfortunately I cannot gather up all the students in the United States that took college algebra and find out what their success rates are. However, I can use a sample and let that sample be a representation of that population. Okay? Because trying to find a population, it will take time and it will take an awful lot of money to do it. So, best to do a sample and let that sample be a representation of a population. Okay. Alright, the next definition is a confidence interval, which is basically what this particular video is about. And the next two videos that I discuss will be on confidence intervals. Okay? Now, because the point estimate is a single value that gives us no indication of how good the best estimate is, then statisticians have cleverly developed what they call a confidence interval, or another way would be an interval estimate. And that consists of a range of values. So, let me go ahead and give you that definition of a confidence interval. It is a range of values that's used to estimate the true value of a population parameter. Okay. So a confidence interval is a range of values that is used to estimate a true value of a population parameter. Okay, and sometimes the confidence interval can be abbreviated as CI. So CI will represent confidence interval. Okay, and also to get a confidence interval, you also need what they call a confidence level. Okay, confidence level. And the confidence level is this. It is the probability and that's going to be, that probability is going to be 1 minus alpha. That's the probability that the confidence interval actually does contain the population parameter. Okay, so the probability that the confidence interval actually does contain the population parameter, that's going to be your confidence level. And that's provided that the estimation process is repeated a large number of times. And sometimes the confidence level can be called the degree of confidence or the confidence coefficient. And the three most common confidence levels are this: 90%, 95%, and 99%. Those three are the most common confidence levels. Okay. And again, there are others that we will be looking at. Okay. Alright, now, what I have up here on the screen is the correct way and the incorrect way of interpreting a confidence interval. Okay? Because when we interpret a confidence interval, we have to be very careful on how we do that, and we have to do it correctly. Okay, so in this example here, let's say our confidence interval is this. P is between 0.828 and 0.872. We have a correct and the incorrect interpretations. The correct interpretation is this. We are 95% confident that the interval from 0.828 to 0.872 actually does contain the true value of the population proportion P. That's the correct interpretation. Now, these are a couple of incorrect interpretations. One incorrect interpretation is this: there is a 95% chance that the true value P will fall between 0.828 and 0.872. That's the incorrect way, because with confidence intervals, we are not dealing with probability. Okay? We're not dealing with probability. The fact is that true proportion will either be in that confidence interval or it will not be in that confidence interval. Okay? And the other incorrect interpretation is this: 95% of the sample proportions will fall between 0.828 and 0.872. That's the incorrect way. Okay? And it is important that the population parameter is a fixed value, which means that that confidence interval limits will either have the population proportion or it does not. Okay? So that's very important how you interpret a confidence interval estimate. Okay, now, another definition that I need to mention is the critical values. Okay, so let me write down critical value as our other definition, because in this case here, when you're trying to find a confidence interval, you're going to be dealing with a critical value. Okay, now the critical value by definition is this. That is the number on the borderline and that number is the one that's separating the sample statistics that are likely to occur from those that are unlikely. Okay. It's going to be that number that's on the borderline. And that number is what separates the sample statistics that are likely to occur from those that are unlikely. Okay, and the notation for that is going to be this. Z sub alpha over 2. Okay. That's the notation, Z sub alpha over 2. And that's the number, that's the critical value that a z-score with the property that it separates the area of alpha over 2 in the right tail of the standard normal distribution. Okay, so if you recall, well, let me go ahead and draw a normal curve. You probably already recall the normal curve from previous videos here. Okay, these shaded areas that will be in green, this area to the left and this area to the right, that's alpha over 2, and this is also alpha over 2. And this number, whatever this is, that separates, that's the borderline, that's Z sub alpha over 2. And this white space in the middle, that's your confidence level. That's going to be the confidence level. Okay. Okay. So now, for the confidence levels, there are critical values that are associated with it. So let me give you those. Okay. The first column is the confidence level. The middle column is your alpha level. And the third column is the critical value. That critical value, of course, is going to be Z. Okay. Now for an 80% confidence level, your alpha level is going to be 0.20. And the way that I get that 0.20, you subtract 1 minus your confidence level. So alpha in this case is going to be 1 minus the confidence level. Okay. And in this case, your critical value for 80% confidence level will be 1.28. Okay. And then for 90%, your alpha level is 0.10. And this critical value will be 1.645. And then for 95%, your alpha level is 0.05. And this confidence level, critical value is 1.96. Okay. And then for 98%, its alpha level is 0.02, and its critical value will be 2.33. And then for 99%, that will be 0.01 for its alpha level. That's 1 minus 0.99, and its critical value will be 2.575. And then 99.8%, its alpha level will be 0.002, and the critical value there will be 3.08. And then finally, 99.9% confidence level will give you an alpha level of 0.001 and a critical value of 3.27. Now, you're not expected to know all of these, and you will not be required to use all of these. However, the ones that you want to be familiar with would be the 90%, 95%, and 99%. Those are the ones that are most commonly used in this particular video. So do keep those in mind. Keep those critical values in mind. Now, I know what you're thinking. Where are these critical values coming from? Okay, here's an example. I'm going to do 90%. So here we have a 90% confidence level. So here the middle is your 90%. Your alpha level is in the shaded area on the left and the shaded area on the right. So this represents alpha over 2. This represents alpha over 2 as well. Alright, we got 90%. The area under the curve is 100%. So if that's 90%, these two represent 10%. But they're both split in half, so that means that your alpha over 2 will be 0.05. And this alpha over 2 will also be 0.05. Okay? Now suppose I want to find the z of alpha over 2. In this case, now if you use your table A-2 or your standard normal distribution table, you know that it's going to be the area, the cumulative area from the left. So if I know this is 0.05 here, this area to the left will have to be 0.9500. And then that's where I use my standard normal distribution table to find 0.9500. Well, guess what? There's a star right here in the middle. That tells me that that area, what I'm looking for is exactly 0.9500. And that z value is 1.645. So that tells me what z of alpha over 2 will be. 1.645. So for a 90%, that critical value is 1.645. Now that's just one example of many. So you pretty much get an idea of where that z of alpha over 2 is, that critical value z is coming from. Okay. Now let's look at a couple of examples of just this, finding the critical value. Okay. Let's say in this case we want to find the critical value z of alpha over 2 that corresponds to the given confidence level. In this case here is 81%. Okay. So if I draw a normal curve looking like this area in the middle is your 81%. That means that this area to the left in green and this area to the right shaded in green represents a total of 19%, or 0.19. So that means this is alpha over 2. That means 0.19 divided by 2 will be, well, I'll go ahead and write it out, 0.19 divided by 2. That will be 0.095. So this area is 0.095. And this area on the left-hand side is also 0.095. Okay. All right, now we want the area to the left. Because if we're going to be using that standard normal distribution table, we want the area to the left. So we got to do 1 minus 0.095. That would give us this area to the left, which is in this case 0.9050. Okay. And then we use our standard normal distribution table and find a value that is closest to 0.9050. In this case here, I'm going to use 0.9049. So in this case here, I'm going to read the row and the column that 0.9049 is in. In this case, that's 1.3 and 0.01. So that means z of alpha over 2 is going to be 1.3 plus 0.01, or 1.31. So this represents your z of alpha over 2, 1.31. Okay. This next example is finding the critical value of z of alpha over 2 that corresponds to alpha is equal to 0.17. Okay. So we know we're finding this area to the right. Okay, because that's what the critical value means. That's what z of alpha over 2 represents. Okay. And this is going to be your alpha over 2. Well, alpha is 0.17. So 0.17 divided by 2 will be 0.085. So this area is 0.085. But if we're going to use the table, we need to find the area to the left. So in this case here, we got to do 1 minus 0.085, which will be 0.9150. And I'm taking this out to 4 decimal places because our table has decimal values to 4 decimal places here. Okay, so we need to find a number using our standard normal distribution table. We need to find a number that's closest to 0.9150. And in this case, I'm going to use 0.9147. So I'm going to read off the row and the column that 0.9147 is in. In this case, that's 1.3 and 0.07. Okay, so my z of alpha over 2 is going to be just 1.3 plus 0.07, or 1.37. Okay, so that's how we find these critical values for those particular confidence levels and for any alpha level that's given to us. Okay. Alright, now let's go and continue with some more definitions, and then we'll look at more examples. Alright, the next definition is going to be the margin of error. And of course, the margin of error is defined by a capital letter E. Okay? So in this case here, the margin of error is going to be the maximum likely difference between the observed, I'm going to use a generic definition, the observed sample statistic, and that statistic can be a proportion or a mean or a variance, well actually a mean or a proportion, and the true value of the population parameter. And that could be a population mean or a population proportion. Okay. But here, with a proportion, that would be the maximum likely difference between the observed sample proportion and the true value of the population proportion. Okay. And it's defined by a capital letter E, and we do have a formula for that, which is this. Capital E is equal to your critical Z value, which is Z of alpha over 2, times the square root of P hat times Q hat divided by N. That represents your margin of error for your population proportion. Okay. Now again, the Z of alpha over 2, that's your critical value. P hat, that's the sample proportion. Now this Q hat, when I say Q hat, is always going to be 1 minus P hat. Once you know P hat, you can easily find out what Q hat is. It's simply 1 minus P hat. N is the sample size that's given. Okay. All right. Now later on we're going to be doing some examples where you have to actually find the margin of error. Okay. So with all of this, we can go ahead and talk about the confidence interval for estimating a population proportion called P. So in this case here, that's the basis of this particular video here. Confidence interval for estimating, and I'm just going to say estimating lowercase p, which is the notation for a population proportion. Okay. Now, there are three requirements for a confidence interval. Number one, you must have a simple random sample. Okay. Of course, a simple random sample is this, that you have a whole population. Each sample of the same size has an equal chance of being selected. Okay, so that's what a simple random sample means. Number two, the binomial conditions are satisfied. Okay. What we mean by the binomial conditions? Well, the binomial distribution conditions have to be satisfied. Okay. And what that means is this, that you have a fixed number of trials, and the trials are independent, and then you have two categories of outcomes, either success or failure, and then your probability has to remain constant for each trial. That's what we mean by the binomial conditions, or the conditions of a binomial distribution. Okay? And then third, must have at least 5 successes and 5 failures. Okay, and in notation, the sample size times the probability of success must be greater than or equal to 5, and n sample size times q, that's the probability for failure, must be greater than or equal to 5 as well. Okay, so those are the 3 requirements that you must have for a confidence interval, to even construct a confidence interval. Okay, now from that we're going to have the format for a confidence interval. The format is this: p hat minus e is going to be less than p and less than p hat plus e. And in this case, e is equal to z of alpha over 2 times the square root of p hat times q hat divided by n. Okay? Because your confidence interval is going to be in this particular format as a compound inequality. Okay? And the round off rule is this: you're going to round your limits to 3 decimal places. You round your limits to 3 decimal places for your confidence interval for a proportion. Okay. Now what I'm going to put up here is the requirements, or the procedure during the confidence interval for P. Number 1, you want to verify the requirements, that the requirements are satisfied. There were 3 of them that I gave you. Number 2, you're going to use, now you don't necessarily have to use a standard normal distribution table. What you can use is this particular chart that I gave you. That will help you find the confidence interval. I mean, actually, you'll get your critical values, and you're going to use those critical values to find the margin of error, which is step number 3. And then step number 4 is to use that particular format that I gave you, the general format. Now, sometimes they may give you another format that looks like this: p hat plus or minus e, or p hat minus e, comma, p hat plus e. That's interval notation. And then round the resulting confidence interval limits to 3 significant digits. Okay, so now let's look at some examples of just this. Okay, let's say we had this. Here we want to use the sample data and the confidence level given below to complete parts A through D. A research institute asked respondents if they felt vulnerable to identity theft. In a poll, N is equal to 1,067 and X is equal to 528 who said yes. Use a 95% confidence level. Okay. Now, in this case here, we're going to start off with part A by finding the best point estimate of a population proportion, which is P. Okay, so here we want the best point estimate. and the best point estimate is always p hat. Now notice that you're given an x and an n that don't give you the actual number. So we have to use this formula: x is x divided by n. So in this case, you're given the number of successes and the sample size. To find p hat, which is your sample proportion, you have to take your x and divide that by n. Okay, that's very important. X is the number of successes, n is the sample size. In this case, x is 528 divided by n, which is 1,067. And if you take your calculator and do 528 divided by 1,067, you will get 0.495. So the best point estimate for this population proportion P will be 0.495. And then part B, they want the value of the margin of error, E. So in this case, E well, before we find out what E is, let's identify what's given to us in this particular situation. Right, in this case here, we found out that p hat was 0.495. We need to know what q hat is. Q hat is going to be 1 minus p hat, or 1 minus 0.495, which will be 0.505. And we know what n is. N is 1,067. Okay, and we're told in the problem to use a 95% confidence level. So, if we have 95% confidence, that means z of alpha over 2, and if we go back to this sheet that I have up here, 95% confidence, that's one of your common confidence levels. So that critical value for 95% will be 1.96. So z of alpha over 2 is 1.96. So from there we can find the margin of error, which is z of alpha over 2 times the square root of p hat times q hat divided by n. And in this case here, z of alpha over 2, your critical z value, that's 1.96, times the square root of p hat, which is 0.495, times q hat, that's 0.505. All that's divided by n of 1,067. Now this we can enter into our graphing calculator. Okay, so if we enter this in the calculator, we type in the critical value of 1.96 times the square root is second and x squared for the square root. And then we can type in 0.495 times 0.505 divided by 1067 and close the parentheses. And then hit enter. Now, I'm going to try to use as many decimal places as I can. In this case, that's going to be 0.0300. And I'm rounding this off to 4 decimal places. Okay? So that's part B, is just finding the margin of error. So your margin of error is 0.0300. Now part C is to construct the confidence interval. Okay, I got p hat, I got my margin of error. So the format is just simply this: p hat minus the margin of error, and that's less than p, and less than p hat plus the margin of error. In this case, p hat was 0.495 minus the margin of error was 0.0300, and that's less than P, and less than. Now I copy these same two numbers, but this time it'll be a plus. So 0.495 plus 0.0300. Because as you can see, one's going to be a plus and the other one's going to be a minus. So if I do 0.495 minus 0.0300, if I round this off to 3 decimal places, that would be 0.465. That's less than P, and less than, in this case, 0.495 plus 0.0300 will be 0.525. So this is my confidence interval. The true proportion is between 0.465 and 0.525. Now in part D, you were asked to write a statement that correctly interprets the confidence interval. We're going to write a statement that correctly interprets the confidence interval. Okay, so now, here's our statement. We are 95% confident that the true value, and this is just generic, of the proportion I'm going to say population proportion lies between 0.465 and 0.525. Now, if you want to be more specific, you can say that we are 95% confident that the true population proportion of respondents who felt vulnerable to identity theft lies between 0.465 and 0.525. Okay, so this is how we construct a confidence interval estimate for a proportion. Okay. Okay, let's look at another example of just this. Alright, let's say a clinical trial tests a method designed to increase the probability of conceiving a girl. In the study, 330 babies were born and 297 of them were girls. Use the sample data to construct a 99% confidence interval estimate of the girls born. Based on the result, does the method appear to be effective? Okay, so let's look at what's given to us. We got 330 babies born, so that's your N, your sample size. And 297 of them were girls. So X is your number of successes, that's 297. Which means P hat, that's of course X divided by N, so you want to keep that in mind. P hat means that the number of successes is divided by your sample size. So in this case here, you're going to have 297 divided by 330. And that's going to be 0.9. So P hat will be 0.9. Well, if P hat is going to be 0.9, Q hat is 1 minus P hat, or 1 minus 0.9, which will be 0.1. So Q hat will be 0.1. And we have a 99% confidence level that we're dealing with. That's one of the 3 most common confidence levels here. So Z of alpha over 2, here 99% means that your critical value will be 2.575. For 99%, Z of alpha over 2, or your critical value is 2.575. Okay? So from here we can do our margin of error. And of course your margin of error, which is your capital letter E, that's Z of alpha over 2. multiplied by the square root of p hat times q hat, all divided by n. And p hat q hat divided by n is all underneath the radical. So in this case here, z of alpha over 2, that's 2.575, times the square root of p hat, which is 0.9, times q hat, that's 0.1, divided by n, that's going to be 330. So in this case here, if we do this on the calculator, 2.575 times second x squared, and then 0.9 times 0.1 divided by 330, close parentheses, hit enter, you're going to get 0.04, let's say 0.043, rounded to 3 decimal places. Okay, so that's going to be the margin of error. Okay, and now we can get our confidence level, confidence interval. That format is p hat minus e, that's less than p, and less than p hat plus e. And in this case here, p hat was 0.9 minus your margin of error, that's 0.043, that's less than p, and less than p hat, which is 0.9, plus e, which is 0.043. Now, 0.9 minus 0.043 will be 0.857, and that's less than p, and less than 0.9 plus 0.043 will be 0.943. Okay. So in this case here, let's go ahead and interpret our confidence interval. And that means this. We are 99% confident that the true, now in this case they want the percentage, they're dealing with the percentage here, so the true percentage of girls born lies between, now if we change 0.857 to a percent, it will be 85.7%. And if we change 0.943 to a decimal, it will be 94.3%. So here we are 99% confident that the true percentage of girls born lies between 85.7% and 94.3%. Okay. Okay. Now hopefully this will be enough examples to at least get you through some of the homework problems that deal with confidence intervals. Okay, the next thing I need to talk about is this. Sometimes it's helpful to get a confidence interval, but we need to know, if we plan on collecting data, we need to know how many sample units must be obtained. So the next thing we're going to look at is determining a required sample size. So here we're determining a required sample size. Okay. And we can find out what that sample size is. And there are a couple of cases if your sample proportion, which is your p hat, is known, if it's given, then we're going to use this formula. N is equal to your critical value, Z of alpha over 2, and that's going to be squared, times p hat times q hat, and that's divided by your margin of error, which is your E, and that's going to be squared. So if your p hat is known, then you can use this formula, Z of alpha over 2 squared times p hat q hat, all that's divided by E squared. Now let's say p hat is unknown. Let's say we don't know what our sample proportion is going to be. In this case, we use this formula, N is equal to Z of alpha over 2, and that's squared, times 0.25, and that's divided by E squared. And the reason why we use 0.25, if it's unknown, then we're going to say that p hat will be 0.5 and q hat will be 0.5. And 0.5 times 0.5 will give you 0.25. Okay? So pretty much you have to pay close attention what they're asking for. Okay, now let's look at one example, or a couple of examples that are related to this. All right, let's start with this one. Use the given data to find the minimum sample size required to estimate a population proportion or percentage. Alright, in this case here, you're given a margin of error of 0.07, the confidence level of 95%, and p hat and q hat are unknown. Okay, so we know what the margin of error is. That's your capital E, 0.07. And we're dealing with a confidence level of 95%. Which means your critical Z value is, in this case, for 95%, your critical Z value, that's your 1.96. Okay, so your Z of alpha over 2 will be 1.96. Now, we're told that p hat and q hat are unknown. So, we're going to have to use this formula, N is equal to Z of alpha over 2, and that's squared, times 0.25 divided by E squared. Okay. Z of alpha over 2 was 1.96, so that's 1.96, and that's squared, times 0.25 divided by E, which is 0.07, and that's squared. And I do need to mention that when you're dealing with the required sample size, that round-off rule is this. Round the N, the value of N, to the next larger whole number. Very important. N needs to be rounded to the next larger whole number in the event your value of N becomes a decimal. Okay? So in this case here, if we do 1.96, and that's squared, times 0.25, then divide that by 0.07 and squared. Now if I hit enter, I was fortunate. I do get a whole number of 196. So here, that sample size required will just simply be 196. Okay? So my minimum sample size that I'm going to need is 1.96. Okay, now another example would be this. let's say many states are considering steps that would help them collect sales taxes on items purchased through the internet. How many randomly selected sales transactions must be surveyed to determine the percentage that transpired over the internet? Assume that we want to be 99% confident that the sample percentage is within 5 percentage points of the true population percentage for all sales transactions. Okay? Now in this case here, we're dealing with a 99% confidence level. And that means Z of alpha over 2, your critical value. I'm going to bring that table back up so y'all can look at it. 99% confidence means that it's going to be 2.575 for your critical value. So your Z of alpha over 2, which is your critical value, that's 2.575. And the margin of error is within 5 percentage points. Now, 5 percentage points as a decimal will be 0.05. That E is not going to be 5. So when it says within 5 percentage points, E is actually 0.05. Because that's like within 5%. So 5% as a decimal is 0.05. And nowhere in this problem were we told what P hat is. So P hat is unknown. So in this case here, we use the formula N is equal to Z of alpha over 2, and that's squared, times 0.25, and all that's divided by E squared. Well, Z of alpha over 2, that's 2.575, and that's squared, times 0.25 divided by E, that's 0.05, and that's squared. And that's equal to 2.575 squared times 0.25 divided by E 0.05 squared. And hit enter. Now this time I came up with a decimal of 663.0625. Now, the rule is for finding a required sample size, you round up to the next larger whole number. So 663.0625, I'm going to round up to 664. Okay, so I'm going to write this out. 663.06, we round it up to 664. So, the minimum sample size required in this case would be 664. Okay, which means 664 randomly selected sales transactions must be surveyed to determine that the percentage that transpired over the internet. Okay. Okay, now let's look at the next example. Use the given data to find the minimum sample size required to estimate the population proportion or percentage. Here the margin of error is 3 percentage points. So here 3 percentage points will be 0.03 and not E is equal to 3. 3%. So 3% as a decimal will be 0.03. The confidence level is going to be 90%. That means your critical value, Z of alpha over 2, for a 90% confidence level, Z of alpha over 2 will be 1.645. And P hat is estimated by the decimal percentage of 58%. So P hat will be 0.58. Okay. Well, if P hat is 0.58, then Q hat is 0.42. That's just simply 1 minus 0.58. Okay? because the p hat and q hat are complements of each other. Okay, p hat is known. That's given to us. So this time, we're going to use this formula. N is equal to z of alpha over 2, that's squared, times p hat times q hat divided by e squared. Okay, because p hat is known. Your z is 1.645. That 1.645 is going to be squared times p hat, which is 0.58, times q hat, that's 0.42, and e is 0.03, and that's squared. Okay, all of this can be typed into the calculator. So here's what we have. We got 1.645, and that's squared, times 0.58 times 0.42, that's divided by 0.03, and that's going to be squared. Okay, and then you're going to hit enter. Now here I'll come up with 732.43. But again, as always, the round off rule for this means you must round up to the next higher number, the next larger whole number. So in this case, 733. So in this case here, the minimum sample size required for this will be 733. Okay, let me do one more of these required sample size, and then I got one more thing to cover on this video. Here we want to find the sample size, which is your N, needed to estimate the percentage of adults who have consulted fortune tellers. Use a 0.08 margin of error, use a confidence interval of 90%, and use results from a prior poll suggesting that 18% of adults have consulted fortune tellers. So in this case here, the margin of error is 0.08, that's going to be your E. We have a 90% confidence level. Okay, which means Z of alpha over 2. So here 90% confidence, meaning Z of alpha over 2 is 1.645. And P hat is known. That's 0.18 from a prior poll, which means Q hat is 1 minus 0.18 or 0.82. Okay, now P hat is known, so that means we can use the formula N is equal to Z of alpha over 2, that's squared, times P hat times Q hat, all that's over E, and that's squared. Now Z of alpha over 2 is 1.645, and that's squared, times your P hat, that's 0.18, times Q hat, that's 0.82, all that's over E, that's 0.08, and that's squared. Okay, putting this in the calculator. 1.645, and then we press x squared to squared times 0.18 times 0.82 divided by 0.08, and that's going to be squared. Then hit enter. So we got 62.41. We round up to the next larger whole number, which will be, in this case, 63. So here, the required sample size needed to estimate the percentage of adults who have consulted fortune tellers would be 63. Okay, so this should be enough to assist you with some of that homework that deals with finding the required sample size. Okay, now the last thing I need to cover in this video is this. let's say we want to find the point estimate and the confidence interval E. And we're already given a confidence interval. So here we want to find your point estimate, which I'm going to call P hat, and E, which is the margin of error, from a confidence interval. Sometimes the confidence interval will be given, but you don't know what P hat and E are going to be. Well, here's an easy way to find out. To find out what P hat is, that's going to be your point estimate for P, or the sample proportion. You take the upper limit of your confidence level. You'll add that to the lower limit of your confidence level. And that sum is going to be divided by 2. Okay, and then for the margin of error, that's your E. You take the upper limit, your upper confidence level interval limit. This time you're going to subtract the lower confidence level limit from your upper limit and divide by 2. Okay, so you'll be using these two right here to come up with your P hat and E. So in this one example that I have here, let's say we want to express the confidence interval of 0.333 less than P and less than 0.555 in the form of P hat plus or minus E. Okay, so in this case here, to find P hat, we take the upper limit plus the lower limit divide by 2. Your upper limit is right here, 0.555. Your lower limit is at 0.333. And then divide by 2. Add 0.555 to 0.333, you're going to get 0.888. Divided by 2 will be 0.444. So P hat will be 0.444. And then E, which is your margin of error, that's going to be the upper limit, this time minus the lower limit, and divide by 2. Your upper limit is still 0.555 minus the lower limit of 0.333. That's divided by 2. Now 0.555 minus 0.333 will be 0.222. Divided by 2 will be 0.111. So your margin of error will be 0.111. Now in the form of P hat plus or minus E, your P hat in this case was 0.444, then plus or minus E, which is 0.111. Okay, so that's how we express that confidence interval in the format of P hat plus or minus E. Okay? Alright, so this should be enough to assist you with all that homework that's in that particular section on estimating a population proportion. And I will conclude this video. Email me if you have questions.